Hey there, and welcome to the next lesson. Here we go. We're looking at applied forces at angles and the new normal force and the net force, the direction of motion. So we're looking at situations of like pulling a wagon or pushing down on a lawnmower, pulling on a box, pulling on a toboggan, that kind of stuff. Okay. So a classic example of pulling a wagon, you have this 200 Newton force at a 50-degree angle to the horizontal. We need to be able to visualize that some of that force, a component of it is sideways and some of it is upwards, right? In this situation, we have the wagon moving straight sideways, accelerating sideways, staying on the ground. So in other words, we're not pulling enough that it's going to lift it. So the acceleration in the y direction 0 is something that we might use, and so on, right? So the net force in the y direction is 0. Often questions will ask in this order: draw a free body diagram, and what's the net vertical force, and so on. I kind of feel like the better order would be this, where you'd analyze forces, determine the values, and then draw the free body diagram. But kind of the point of the free body diagram is to help visualize things, so I get why a lot of times they ask for it first. But if you don't know the sizes, you just have to sort of draw arrows pointing in the right directions, I guess, maybe at least, hopefully. And then maybe adjust the sizes later. Anyways, so for me, I'm thinking, okay, well, like we said, the acceleration in the y direction is 0. So we know the net force in the y direction is 0. And we know net force is a bunch of forces added up. Well, what forces are there what forces would you have on a free body diagram? You're going to have gravity. You're going to have the normal force, the sand is pushing up on the wheels, and you're going to have the vertical component of the applied force, right? So there we go. We got your gravity, you got the normal force, and you got the vertical component of the applied force. So in this question, I just did the component work in line with the question. In this one, I asked specifically in this question for the components separately, so they were done separately. Either way, it basically works as long as you're pretty thorough about things. So notice that opposite side of the triangle here, we've got your y component, so that's why we used sine. So 200 times sine of 50, right? That's totally okay to do. That's a shortcut that physics people, you do all the time. You don't have to start with sine of 50 equals opposite over hypotenuse and then solve and so on. It's the same solving process every time leads to that consistent answer. Opposite, use sine. And our gravity force is the negative 9.8 times 30, negative meaning down in this case, and this one's positive meaning up, of course, because of the direction we're pulling. So we end up with those numbers, and we just basically combine them and then add to both sides, or subtract this one from both sides and add that one to both sides, however you want to think of it. Okay, so that's what I did there, giving us a normal force of 140.8 newtons or so. And notice the positive number means it's up, right? So that's A. What's the net vertical? I guess that was A right there, right? Net vertical force is up, and then B was what determined the normal force. And then finally, now that we have those values, you can draw a free body diagram. We're going to have a gravity force down of 294, so almost 300, a normal force up of around half of that or so, and then the applied force of around half of that too, right? So it looks kind of like that. So I want you to think of, sometimes people might draw the two forces like side by side on the free body diagram. I think it's a little clearer when you show it like that. The other thing we can do too is we can look at those two forces. I can just highlight those. Actually, it's going to grab the other one with it, but that's okay. So if I were to, wrong button I'm holding here, if I were to just move those down here, you can see like they're the same size as that gravity force, right? So that's what I showed there too, right? That this is the same as the negative of the gravity. So in this case, negative of negative means, right? Negative of down means up, and so on. Note here, the normal force would be 294 if you weren't pulling on it. So pulling up reduced that normal force, right? All right. Acceleration horizontally, so determine the net force horizontally, of course, right? So the net force horizontally is, I got backwards releasing here of things going on. But, oh, it says if the acceleration, sorry, that's why. If the acceleration is to determine the net force, right? That's using acceleration to get the net force. And so, yeah, we just multiply mass times acceleration. So it gives us a net force of 60 newtons. And so it's saying, like, how much friction is there then if that's the net force based on the observed acceleration? The net force horizontally is, of course, made up of all the forces on it, right? So there's a friction force and there's the applied force. And so the applied force would be the cos, right? Because we're adjacent to the 50. So it's going to be cosine of, there we go, it's going to be cosine of 50 times the 200. Okay, so you have the 60 plus that friction force gives that, or added to the 128 is a true equation here, right? So you subtract the 128.6 from both sides, end up with the friction force being negative 68.6. The negative in this case meaning, of course, the opposite direction of the acceleration, the motion, I should say. But anyways, all right. So that is in a lifting situation. In a pushing down situation, so we've got an applied force of 25 newtons at 60 degrees to the vertical. How the words might have been read there. Force is directed at downwards at an angle of 60 degrees. That's maybe not clear enough, but the picture clears it up. And we have a friction force of 10 newtons. And yeah, so determine the x and y components. That's easy enough, right? X component, y component. In this case, our x component is obviously there, right? Or you could think of it as here. But if I want to think of it relative to that angle, it's the opposite side of the 60. And so we're doing sine of 60 times the 25. Works out to be that. 21.65 dot, dot, dot. If I round that, it really technically goes to 21.6. That's our even rounding rule, so that we're not rounding up more often than down. And of course, we know that it's to the right based on the picture. And then the y component, if we put it there, then that you can tell it's adjacent to the 60. So we're looking at cosine of 60 times that 25. Giving us that value. And now I wrote in down, obviously in the net force realm of things, would be a negative number, right? So that's what we'll do next to determine the normal force on the block. So we know that it's not accelerating, it's sitting on a level surface. So we know the net force is 0. So right there, we know net force is 0. And then of course we know the net force is all the forces added up. So we've got a gravity force, we have the applied force down, and we have a normal force up, which will be in the diagram here later on, right? But yeah, gravity, normal force, and applied force. So we've got the gravity force, m times g. So we have that number. I slipped a little negative in there because I forgot it at first. The normal force that we're wondering about, and then the applied force goes in as a negative value because it's down. And that leaves us with what here? So we're going to take that 49 number that we get from the gravity, and we're going to add it to both sides, and add the 12.5 to both sides, and end up with a value of 61.5 newtons up. Note in this case that the push down, of course, increased the normal force. I think it's probably pretty intuitive, but it's nice to see the numbers working out, right? Free body diagram of this thing. So we've got our, what do we have? We have our gravity, would be the easiest one to pinpoint, right? And then everything else relative to it, maybe. So we need a normal force bigger than that. And then we have the applied force down. And the idea is same thing here, right? That normal force balances balances the combination of those, right? So I have to clone it, not just steal it. There we go. So that is components, normal force, and now we're going to get the acceleration of the block. So acceleration of the block, of course, we're looking at horizontal motion because we're on a flat surface here. So that's our net force. And so our net force is the 21.65. And of course, F net equals ma, right? So F net equals ma, divide out your 5, gives you the acceleration. Therefore, and so on. I would have my units in here, of course, maybe seconds squared and to the right and so on. I don't want you to think that I'm not to show that stuff, I'd probably normally put units there too. If there's no directions ever, I would fault it. But if the directions and the units are in the therefore statement, then that's okay too. But I could picture maybe someone saying like, should have a direction there too, maybe. But as long as it's there, then you're safe. Okay. Yeah. So I mentioned earlier here the idea of like not pulling too hard, right? So that we still have this acceleration in the y direction 0. Just a quick look at what would happen if you pulled too hard. You can tell this seriously could be a picture of me with my first daughter. It looks like my arm and it looks like her, but it's not. It's just from the internet. But if we pull this dad, you can tell he's going to pull hard, and this kid's anticipating it, right? So if you pull really hard, then you end up with a net force up, and it causes acceleration, in the direction of that net force. So you'd actually take the no problem. You'd actually take the two forces, you'd add them up, and you'd end up with acceleration in that direction, right? So you'd have your net force, and you can picture the way it would go for at least a little bit, right? So resulting acceleration and so on. There's my diagram. Good stuff. All right. Thanks for watching. Hope that makes sense. If you need any help, take advantage of the opportunities there. You got the post help section, you've got emails, you've got all sorts of stuff. All right. Talk to you later. Thanks for watching.